Okay, so today I've been seeing two things, right? You have seen virtualization first, the complexities that goes in, and the kind of uh, things you get out of it, right? And then we also saw containers. We had a kind of a hands-on introduction to containers using Docker. So that's a common way to run containers, but there are other ways. Priyanka mentioned, Kavya mentioned. There are other container engines or container runtimes. Right? So this session, we are going to look one level deeper, right, and understand what are the building blocks of this container technology, right? That's the aim today. So this is just a recap image. You have seen this a few times. You have the entire guest OS, and the hypervisor is the one that's actually running the VM in case of virtualization. In case of containers, you don't have any of that, right? You don't have an hypervisor, special hypervisor, right? And also the containers don't actually have the full entire guest OS, right? But this can't just work like that. It can't just magically work like that, right? Something has to make this containerization possible, right? So we have said there's a host operating system, and then we have just shown you the containers on top of that, right? But something in the host operating system has to make this containers work, right? Otherwise, how are we doing this? So this is a brief timeline of the container technology itself, right? It didn't come out in a day. There are a lot of different things that came together, and it kind of evolved into what we have today, right? So today, if you see I mean, it's like the most common way to run applications is using containers, right? But we have gone through this whole journey, and containers have also improved over time and into the form that they are today. So the first occurrence that you see here on the left is leftmost thing, which is like the concept of FreeBSD jails, right? So the thing you have to note here is FreeBSD is a different operating system, right? It's not Linux, right? So not all containers are Linux containers, but today when you talk about containers, it's just assumed to be Linux containers. You can actually have containers on each and every operating system. There are something called Windows containers also, but that's a topic for another day, right? So this first version of containers was actually called jails on FreeBSD, and that was some kind of wrapper on an existing technology called chroot, right? That's what you see here. And then there is a number of iterations that has gone through where ideas were lifted from one operating system to another operating system, right? So if you look at this Solaris zones, this is yet another important point in time where Solaris is a different operating system, right? It's not doing the same thing that FreeBSD is doing, but they have kind of introduced a concept that can be called as a precursor to containers using what they call the snapshots. Right? So eventually things like kind of added together. So the next important milestone is this C groups. This is introduced from Google, and this has gone. This was for Linux the first time, right? And then we have Red Hat introducing namespaces. This is yet another concept. So containers today are built on top of all these concepts, right? So if you go back to 2004, what was containers then was very different from what containers today. And then finally in 2008, we have this LXC project, which is basically bringing all these technologies into one platform, one API, so you can actually create containers, destroy containers, and do all of this stuff with these diverse technologies. And Docker kind of actually built the layer on top, which is the user-facing, easy to use, pull, push build that you saw today. That is kind of the more outer or user-facing, layer. So Docker built on top of LXC. All of these technologies are building on top of each other, right? So we have seen Docker today. So in this session, we are going to look at C groups, namespaces, and chroot, right? That's the idea. Containers are made of more. There are some more technologies that make containers, but we'll focus on these three key pieces, right? So again, full hands-on, so you can kind of start. So in Linux, right, if you know the slash, this is the topmost folder in your file system hierarchy. It's important because that's kind of structuring what you can do on the system, right? If you see when you run a program like bash, it's somewhere in user bin or slash bin or somewhere like that, right? And the operating system, this is the convention the operating system is using to place things like binaries, things like where you mount your volumes, things like where configuration files should be. If you see this example, I hope many of you have seen it. You can right now run this command on your Linux VM and see this kind of top level hierarchy, right? You should see all of these folders. These are common. These are the same standard things, right? They are all used for particular purposes. Lib and lib64 is to actually keep your dynamic libraries, right? So this is the high level root. This is what is called as root of the file system, right? And chroot, the command, this is the core first piece of technology that kind of builds containers, just changes the root for a particular process to a different folder, right? So now if you do ls slash, this is what you will see, right? But if you use chroot on a process, that process will not be able to see all of this. Instead, it will see only what you ask, what you give to it, right? And that's the first step towards making a process, isolating a process, if you think about it, right? Because right now, when you run a program, you can access all the libraries in the system, you can access all the files, all the programs, all of this stuff, right? But once you limit a program to a particular root directory, it can't come out of it, right? What it sees, what its view of the world is just that, right? So this is like, if you just think about it, if you just use chroot today, don't use containers, don't use Docker, the chroot command line is available, you can run it today. So what is the benefit of it, right? It is useful for a number of things, like say, just for testing different versions of software, right? You install some version of Python. This is a way to install a different version and give that version to a particular program, and that program is not aware of any other version, right? And this is an example, but you can do all sorts of things like this is usually used in development, and essentially your entire distro, what you call as a distro, operating system distribution in Linux. You're rid of Arch, you're rid of Manjaro, you're rid of Debian. So all of these have different file top level structures, and using this you can actually kind of give a program a different distro's view on your own computer without changing anything else, right? You're not changing your distro, you're still running the same kernel, but you can kind of give it that view, right? That's kind of what happens inside these containers also, but just with chroot you can do it, right? But it's also important to know that you can't do anything else with chroot. So the processes can still have the same powers. There is no limits on, say, how much compute they can use, or if it has root, it can actually do some things to get out also, right? It's not really isolation proper, but it's a first step towards it, because you're giving a limited file system view, right? So yeah, so we are going to try out a jail, try out a chroot. A jail is more than chroot, but let's just call it that, right? So just create an empty directory jail1 or something in your local folder, and just run sudo chroot jail1 and see what happens.
Just to note, right, this is not inside the Docker container. You can just run it on the VM or your host if it has Linux.
It failed to run something, right? So what is happening is you're saying I want to switch to this new folder. That folder is empty. It has nothing. And you're asking it, by default it runs bash, right? But there is no bash in that folder. That's all is the view of the world for that process you're starting, and it's not able to do, right? So let's rectify that by copying bash, the binary, into that folder, right? So essentially, like you can just add a bin folder inside that jail1 folder, and then copy your bash, and then try to run chroot again. You can open that PDF and you can just copy paste if you want to save some time. Some of the commands down the line will become longer. So when you use the chroot command, right, that's basically a user space program that you're using. Internally, Linux will actually execute using some syscalls, using some libraries, whatever, right? So end of the day, when you use Docker, somewhere inside Docker is calling the same system libraries or syscall or whatever.
Okay. In typical Linux systems, bash is like dynamically linked with this LB. Yeah. So if it was statically, it would work, but I think we have to note that. I mean, we have to add that to the whole lib64 or lib32.
Yes, yes. So if you run the file command on bash, you'll see what he's talking about. It will print about the the executable itself, and it will say somewhere there dynamically linked, right? Are you able to see that? Are you able to see the word dynamically linked? So basically, this is like basic Linux structure where most of your programs are dynamically linked, right? So in the sense, they don't have everything they need to run. They depend on some other libraries, and at runtime, you link the libraries, right? The operating system does that for you. So now in this case, what we have done is we have not given it the libraries, like we have chrooted into this folder, and this folder only has that bash and it doesn't have the libraries. So normally these libraries are in /lib or /lib64. This is what I was talking about earlier. So this set of commands, I explain what this is doing, but what we are trying to do is we are copying all the library dependencies into that jail folder, right? So before running this whole thing, right, just run that middle portion, ldd/bin/bash. Just run this. So if you run this, this is the linker's output of its view of what are the other libraries that this particular binary needs, right? You're able to see 3 or 4 entries. Are you able to see the libraries, dependencies, right? So then you can run the full 3 commands I've given here. So what we are doing is we are just recursively looking for all those dependencies, copying them into that jail folder, right? So if you run the first two commands, then just look at the folder in jail1, right? See what are the files you have. There should be a bin folder, there should be a lib folder, whatever, right? That relevant portion has to be copied. So the first line is just listing it and then just plucking out the library paths, right? So if after the first line, if you do echo $list, you will get that list, right? And the second command is just looping over them and copying them with that folder structure, right? So if there is a file lib64 something, it is creating the lib64 inside jail1 and then copying that file. So when you are done with the first two commands, if you just do ls jail1, you should see bin lib64 out of this. Are we good? Are you able to run? Are you able to get the bash shell this time? So bash is running. Okay. So now if you just try to do ls there, right? Try ls in that bash shell. See what happens. Is it working? No. Try to do cd, like cd, you know that there is a lib folder there, right? So try to do cd/lib. Okay. So essentially bash is running, but you can't run other commands because the same problem happens there, right? You don't have the other commands. You have to again get their dependencies, so on and so forth, right? Clearly. So just for completeness, because on this topic, you can instead look at static binaries. It's so difficult to get all the libraries for a dynamically linked program. As an alternative, if you have a statically linked program, it's an all-in-one contained package, right? Any statically linked binary is just on, you can just move that on its own as long as the architecture is the same. I can take it from my laptop to your laptop, it will work, right? So if you know, BusyBox is an example of such a tool. It's like a debugging tool. It has lot of tools. It has all the common commands that you use, right? ls, copy, all of that stuff. In one package, right, as a static binary. So if you just wget that and move it inside to your jail user bin, you'll pretty much have a fully working shell after that because you have all of the statically compared. You don't have to run this. I'm just showing this for completeness, right? So this is an easy way to get around. But obviously, when you build containers, what you do is you actually bring in the full operating system distro file hierarchy, right? You bring in all the dependencies. When you normally do say apt-get install, it's actually able to get all the dependencies and pull them in, right? So when you build a container, build an image also, you do the same thing there. You bring in all the relevant files and libraries that you need, right? So all of that is packaged into that folder, and then you just do chroot to do it, and you're good to go, right? So if you are interested in this offline, this is yet one more thing to see. Essentially, there is some of these commands, deb bootstrap and stuff, which allow you to kind of do that thing I was just talking about, right? You can actually just run the deb bootstrap command and get on your local folder in your computer, kind of a file path / file path that you normally have on a particular version of, say, Ubuntu or Debian or Fedora. You might be on a Fedora machine and you can actually get a folder which is an Ubuntu, any version, right? Any version that you want. And if you do chroot into it, any command you run will be like pretty much as if you're running that operating system, right? So you can see it's like you're not changing anything that you're running. Your kernel is the same, everything's the same, but this is one step towards containers, right? So in containers, you can run in that from command. You can actually build on any operating system distro, right? So you can build from Ubuntu, you can build from Fedora, and end of the day, you can run it on whatever Linux machine you have. It'll all work as if it's running there, right? That's the folder structure that you get. So we are kind of done with the first portion. Let's go to the next building block, right? C groups. So essentially each of these building blocks is doing a different thing, right? So what is C group doing? Specifically, it's doing this one thing of resource control, resource limit, right? How much can that process or set of process see, how much they can use, and essentially ensure they stay within that boundary, right? So you can kind of, again, just to make it very hands-on, just go and run this command, ls sys c group, right? This is kind of the C group hierarchy that is mounted on your system, and you can just look at it to get an idea, right, of the various C group subsystems that exist. Are you able to run this command? Just run this command and see that it's okay. So every folder here is a separate C group subsystem, right? It's a separate resource. So internally, C group is obviously implemented in Linux kernel, like we saw earlier, but it's just exposing this view to you to both see and to control your hierarchy, right? So Each of these folders is a different resource. So you can see there's a CPU here, you can see there is a memory here, these are the kind of common ones. You can see there's PIDs here. Each of them is a separate resource that your process or group of process get. So this output is actually just listing these various C group subsystems on your system, right? So these are different resources that your kernel is able to restrict, right? So these are different dimensions. So you have, like I showed you, right? CPU is a different dimension, memory is a different dimension. So you can control them and limit them independently. For a single container, you can choose to limit CPU to a certain level, memory to some other level, right? So that's why these are separate subsystems. Okay. So I use the word hierarchy a few times. That's because it's like C group is a nested tree kind of structure. So inside a C group there can be another C group and so on and so forth. So this is because you are not dealing with individual process, right? You're dealing with groups of process. So essentially one group of process can be assigned to a C group, and then you can again subdivide and go deeper and say, oh, 4 of these. Actually no, I want to go and assign a specific sub C group to those 4 processes, right? You can build a full hierarchy, and this, like here if you see, these are the different dimensions, right? This is obvious. So memory is completely different from CPU. These are two different parts of the tree. But within that, you can have different groups. Here is one group here called web service, but you can have other groups. Maybe you want a different set of rules to apply to your database service or some other service, right? So you can create multiple of these things. And at the end, at the bottom, you have the leaf nodes, so the processes, right? PIDs are like attached to these C groups. And obviously, as you can see here, they can repeat across the different subsystems, right? Obvious, makes sense. You can attach a particular PID to some particular memory C group and some other CPU C group, right? These are two different dimensions. So just go down into that CPU. So the entire hierarchy is mounted as in that file system there. So just in that sysfsc group, this is the top level. You can just cd to that directory if you want. And inside that, just look at the CPU subsystem. Just do an ls there, and you'll see a bunch of files. I want you to confirm that you're seeing the similar kind of things on your system as mine. My current version. This one is the older 4.5 series. It is changed. Yeah, some things have changed. Which is why I was asking. I wanted you guys to confirm. Yes, V2. There's a V2 also.
What are you using?
So I'm not sure if this was V1 or V2.
So I think this is V2.
Okay, but V2 is, I mean, ideally, if mine older kernel has V2, then everybody should have V2. But that's all.
It depends.
It depends, right?
So in this,
Okay, go back. Essentially, okay, go down. Is there a file Docker here? Docker.service. There is a container D. There's a Docker.service. Okay, what is this path? I'll let others also do.
this one,
System.slice. Okay. So the way C groups are, so the way individual systems are managed can be different. So sometimes you have system D managing the C groups and all sorts of variants. So your structure may not look exactly like this. If you have a folder called system.slice in your top level C group, go into that and just look for docker.slice. But how many of you have a system which looks like mine, right? Show of hands. Anyone? Few people have. Okay. And can others kind of confirm if you have the systemd.slice, system.slice and user.slice? Okay. 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 Then just go into system.slice and there is a docker.service or something. You can go there. Anyway, if you see the files in this folder, right? So there are two kinds of files here. One set of files are these status or control files. So if you say things like this file, this is basically just indicating how much of that system you're using, right? It's like a status. It's like a way for you to know what is going on, right? And you also have some set of files which are kind of controlled. So if you look at this, so this is a file that actually shows what's your current quota, but like everything else in the sys file system, you can actually edit that file and have it reflect on your running processes C groups, right? So what I'm saying is there are a number of files here which show the status of what the C group is doing right now, and there are a number of files here by which you can control the C group, And you also have this actual, this kind of folders, which are the lower levels in the C group hierarchy, right? So if you are able to see a Docker folder, go into the Docker folder. It might be in different place for different people, but go into the folder. So while you're doing this in a separate terminal, you can just check with Docker PS, are you running a Docker container? If not, can you just start the Docker container? You can run the same thing we ran earlier today, nginx. Same command, you can just run any one of those commands. We just want one Docker container to be running. Are you able to see a folder or file folder like this? So you can actually correlate that this is the container by doing a Docker inspect on that container. This ID should show up as the ID of the container, right? So essentially internally Docker has gone ahead and created a subtree there with the name of that container for each container. So if you run one more container, you will see one more folder here. And the way it's organizing it, it's just putting all the Docker containers into a top level thing called this Docker or docker.slice. So for some of you who are on the unified C group hierarchy version, there will be a system.slice, inside there will be docker.service, and inside that you might actually see files for various different subsystems in one folder, right? You will be able to see memory, CPU, UHTLB, all of that in one place, right? It's the same as this, it's just that the way the file system is organized is different, right? So here, this is the portion where the subsystem is mentioned. There it's just mixed into one. This is some version V1, V2 and management difference, but the concept is the same. End of the day, you will have one folder here with the same name as the Docker ID. You can use that code. The exact file folder name might be different. Okay, are we good? We go to the next step. So this is just showing the ls output inside. This is the same set of files you have been seeing, right? This is the same set of files which are there in every level of the hierarchy. But in some sense, we have kind of reached to the very leaf of the tree, right? There is no subfolder here because it's within that Docker container, they all have the same C group for CPU in this case. And if you see the, I believe, cgroup.procs file, right? I think that has the PIDs of the processes in this C group. If we just cat, you can just cat cgroup.procs, this one. Are you able to see the processes? There should be one, I don't know how many processes depending on what we ran. So in general, to look at the C group membership of any process, right? So you can just cat, so this proc file system is another special file system. We just saw this /sys file system. Similarly, this proc file system is a special file system. You can get all sorts of information about processes. So if you just cat this file, you can get the exact C group membership of that PID, right? If you don't know the PID, if you run this, right, it just does it for its own PID, which is in process. In this case, it's just cat, right? Or actually not cat, in the shell. But just run this command and see the output, right? You should be able to see the C groups that this process has been assigned, right? There should be one of each of the different resources, or it might be none if you're just running a normal process. So what you can do to confirm this is, you can run this cat command once outside from your Linux machine, and then run the same command inside a Docker, the container you're running, right? So use docker exec. So I don't know if we covered this in the morning slot. Do docker exec of the container name -it. So I've just given the example of the exec command at the bottom. You can get a shell inside that running container, this nginx container. Try to run the same cat command inside and outside and see the difference. So this list is essentially the list of C groups that Docker has created when it creates a container and then assigns to the PIDs inside the container, right? This is how you're kind of isolating them. So if you run PS, you can just get the list of all processes. If you want to use that to look at the C group hierarchy of some other random process in your system, you can do that. Most normal process in a system probably is not using any C group, so it will all come out to be empty or the top level. Okay, let's go to the next step. So now if you see that container you're in, right? So you are already in the CPU hierarchy. You can just cat this file and see the value, right? So this is the quota that has been assigned for that all the processes in that C group. Just look at the value. What is the value? I want someone to tell me the value for this Docker container that we have created. So those of you on this, my kind of system, have you seen this file? Are you able to see this file? Okay. Those of you who are on the unified system, you will have a different file, cpu.max, right? In that, they should be they should just be max. It should be written max. There will be 2 entries there, but you can see. So, but now the thing to try here is run another Docker, run the same Docker container if you want, run another instance. Just give the CPU's flag, right? Just dash CPUs 2 or 3, right? So what you're telling Docker is you're asking it to limit the CPUs that container will take to that 2 or 3 or whatever, and that number will reflect in this file, right? This file will now have a different number. When we first created, it didn't have any limit, so either you'll have -1 or you'll have max or something like that. When you create it with the limit, you can actually see that number reflected in that file, right? That's what this is supposed to show. So essentially, to show this in action, right? Just to show you that this is not just a number. So just to kind of prove to you that it's working, right? So you say CPU is 2, but then like, is it actually working, right? So you can do this easy test. So this command that I've given here runs something called stressng, which is a stressor. It just runs some busy matrix multiplication kind of thing. It just takes away all your CPU cores. So if you just run the first command, it will actually create 2 workers. So it should technically take 200% of your CPU. That is 2 cores, right? And you can check that by just running top, and you should be able to see that this comes up, right? And you can do this twice. Just change the CPU limit there from 2 to 1 or 2 or 0 and see what happens, right? You should be able to see that the top output is changing. So just try it first with the thing that I've shown, which is 2. You're running 2 workers and you're not giving you any limit, right? Sorry, you're giving limit of 2. So this CPU 2 is a flag to stressng, right? It's asking you to run 2 workers. Separately, you need to add the CPU's flag here, right? So essentially like this, CPU's to 1 or something like this. So these are 2 different flags. But what you want to do is run the container, use top and see that it's consuming so much CPU, and then run it with the limit of 1 and see that it's actually consuming lesser CPU. Has anyone run top and seen the results? Able to see the results? Top is showing 50% to 2 workers. So essentially it creates 2 workers. This is this 2. So stressng is trying to create 2 processes, and each process will go full, all out, right? Maximum core usage. So that normally if you just run just like that, it will take 200%, 2 cores. And then set a limit to 1, then your total processes within the container should use that. This is the C group in action, right? You can actually see the limit being applied. So just to show that you can actually edit this FSC group is actually a live folder, right? So you can actually go change things there, and that will impact your running container. So in this example, I have just used another different C group. Maybe we can skip this example and go to. So actually, it's your choice. We have 2 examples here. One with PIDs. So PIDs is essentially the number of processes you can run in a Docker container, right? So you can limit even that, so that it doesn't fork and create too many workers. So when you run Nginx, right, you should have seen that a lot of workers were created. So I don't know if those were threads, but if they were processes, then they were taking up that many PIDs, right? So you can essentially say, no, I will only allow you to run these many processes. That's the PID C group. And memory is also very obvious, right? There's a memory C group which is just going to directly limit memory, right? So I leave it to you. Both examples are here. We can try any one. But the idea is once you set that, you can actually edit the limit for all of them, even for CPU, right? You can actually go in and you can yourself change the limit there in that hierarchy. And once you change it, that it will immediately apply. So for the PID example, here what we have done here is we have just tried to create some sub processes, right? So when you do this pipe and subshell, it actually ends up creating 2 or 3 forks. So there would be like 3 processes when you run that. And by default, obviously there is no limit, but if you set a limit of 2, then you try to run the same command, it will crash. The container will just go, right? It will try to exceed its limit and it's not working. So same thing applies to memory, right? So memory, there's a limit in bytes. By default, it's not set. You can set it like CPU's flag, there is a memory flag. You can set that. You can change that dynamically just for fun. And you can see that you just try to run any program, just reduce a small limit and then try to run a program, it will crash. And you will see an OM kill message in your usage. You can try any one of these examples. So you might have a question that we didn't have this problem with CPU, right? So when you ran the CPU stressng, it was taking 2 workers, taking 200% CPU, but you could see that it was only it was not crashing the program, right? It's running. That's because CPU is a kind of special in that way, right? That if a process asks you more CPU and you're not giving it, it actually just slows down the process. There is nothing, I mean, there's nothing bad that kind of happens, right? But for memory and things like that, it's like you can't really you can't go down, right? If it wants more memory, it can't really if it asks for more memory, either you give it or you have to shut the process down. The process, what can it do without lesser memory? Right? It can't. So you can just try this any one of these. You can try the PIDs. It might be easy one. Or we can kind of move to the next subsystem namespace. So as before, like I said, some files give you the stats. So this usage in bytes give you the actual memory being used right now by that container, by that C group. And if you change it, you can't change this. You have to change the other one, right? The limit in bytes. Okay, so there was some confusion with versions and stuff, but hopefully you got the idea of how the C group hierarchy is mounted, how Docker controls it, how you can control it, and how it can be used to limit the resources in various dimensions, right? So we'll go to the next piece, which is namespaces, right? So I have a simple two screenshots. So I just want you to see that two screenshots and tell me what's the difference in this context, right? This is one. This is, I just searched for PyTorch on pip, right? The PyPI website. And this is the same PyTorch search on GitHub, right? Obviously, they're not same. One is a package, one is source code. But what do you think is the difference between these two, right? Between these two screenshots? Anything? Any guesses? Right. Okay. Okay. Yeah. Okay. Any other guesses? Yeah. No, yeah, that's true. Leave that aside. This is source code, this is binary, right? So they're not the same kind of thing. But anything else you're seeing in the results, right? If you just look at the results. Anything else sticking out? Yes. So that was kind of what it's looking for. So if you see here, if you just search for packages, it just gives you packages with a single name, right? All the packages you see, there's one name in the package. That's it, right? And it's doing search. But if you see the results in GitHub, it's actually like two names, right? There's a A/B format. There is a organization or a project / repo name, right? So there's a small difference. This difference is actually is namespace, right? I just wanted to give a very layman explanation of namespace, right? So in short, pip doesn't have a namespace, right? Everything is one global namespace. Whatever you do, anybody can push a package with any name and it goes to one global namespace. Everything is there, right? But in GitHub, the organization is around namespaces based on repos or project names or orgs, right? So each of them is a separate namespace. So for instance, here the first result is from the PyTorch org, right? And they might have many repos. The second is from some other group, somebody else. Third is some random person, right? But I can, if I push tomorrow, right, it will just be Chander G / something, right? I cannot push to PyTorch / PyTorch, right? That difference is the namespace, right? That is a kind of isolation. That's exactly what the Linux namespace also do, something similar, obviously, not exactly. So we have seen resource limiting, right? And we have seen certain kind of isolation with the ch root, but this is like real isolation, right? Real processing where you don't get to see beyond the thing that has been given to you, right? So there are kind of 8 namespaces. You don't have to go to the full details, but I will just talk about the big ones, the obvious ones, right? So mount namespace is very clear what part of the file system you can see. It's a bit like chroot, but chroot is about actually switching it, right? Mount is just about all the other file systems. PID, process IDs, right? What is the PID that you're seeing? What is the PID that others can see? If there's a process inside a container, somebody in another container should not be able to see it, right? That visibility should not be there, right? That's the idea there. Similarly with network, right? So all of the networking aspects. We will go into full depth on this tomorrow. Entire day tomorrow is about networking. But this thing is to just show you that there's a network namespace which is isolating the network view of that container as opposed to other containers, right? Or opposed to the host. What the container sees is not what the host sees, and vice versa. There are some more namespaces. The third one is maybe a bit confusing, but it's actually namespace, right? It's essentially what kind of C groups can this particular namespace see, right? Just to point out, similarly, there's a namespace for time. Again, it's not as exciting as it looks. You can't use time to change a system time or something, right? It's just for relative time. It's not for absolute time. Right? So these, I mean, all of them are used, but the first 3, 4 are what is majorly goes. What you kind of see when you run containers, right? You can obviously see these things. They impact you, right? So as before, we are going to do some hands-on to see the namespace and see the differences in namespace, right? So what we're going to do, this is actually about PID namespace, to see the PID view, right? So we're going to run a container and then run a process inside the container, and then look at that process both from inside the container and from outside the container, right? And we want to see essentially what is the PID view, right, within the container and outside. So essentially the first line is just running a basic Docker container using the image called Alpine. It's just, think of it as a very minimal Linux distribution, right? It's just that. You can run anything. You can run Nginx also if you want, right? So the second line is running NC. I think we talked about NC in one of yesterday's session. But essentially it's just, think of it like a lightweight server kind of thing that you're running, just so that we can have a process, right? You can run some other process also. I just chose NC because you will not have NC normally running on your system. So then when you search for the process using PSAUX, there should ideally be only one NC, the one which is inside the container, and not something the system is running, right? And your PSAUX command is just going to list all the processes, right? So you can run this command outside, and that will list all the processes on your Linux machine. There will be many of them. You will have to do some grep to get the NC entry there. If you run it on the inside of the container, you should only see the ones inside the container, right? Which should be much lesser, right? That's what we want to show. So if you see this, right, we didn't talk about this today in detail, but so these flags we kind of give to be able to have that shell open, right? It just says interactive terminal. So this is the only way to have stdin and logged into that. So you can actually run commands, right? And this one is to basically auto delete, remove the container when it's done. So that way if you just exit, it will clean up the container. You don't have to do docker stop, docker rm, and all those things. Are people able to see the difference in PSOX output? Are you able to see the same process in both places? Why is that? Like, can you guess? We put the process inside a container and we wanted to isolate it, but now we are able to see it in both places. So essentially the reason is you're running it on the host, right? So the host is kind of root or super user, or essentially the host is the one that is running all the containers. So the PID, at least the PID namespace, the host can see everything of all containers, but from within each container you can only see the process in that container. So if you run 2 containers and do PSOX in each of those containers, you will not be able to see the same thing. You will not be able to even see those processes. That is the isolation that we're going for. So we didn't go into this in detail, but containers can run more than one process, right? So today morning when we were running Nginx started up, created 4 or 5 workers, and then it was running, right? So that means there are like what? Say let's say 10 processes, assuming that Nginx is using worker processes instead of threads, right? So you have 10 processes running inside that container. You can always do this exec and open extra shells and terminals inside that container, right? And once you have a shell, you can again fork and run any number of processes. So it's not that at any point the container is limited to one process, but there is the process tree. Actually, that should be obvious when you run the PSOX output. There would be a 1, there would be PID 1, right? So in general, on Linux, PID 1 is special. It's the root of the tree. You kill that PID 1, everything goes, right? It's kind of deleting everything. So inside the container 2, it's the same, except now in that PID namespace, 1 is the first process which was created in the command that we gave in the entry point, right? That becomes the PID 1 for that PID namespace. So if you kill that process again, the entire container will go. As opposed to say if you just kill one of the Nginx workers, it won't disturb the other one. So it's the same process hierarchy tree that you have on your host inside the container also, except that it's a separate namespace, a subset, right? From outside you can see everything, from inside you only see that what it is. Okay, so I'm just going to be brief about the rest of the few slides that are left. So we saw the namespace. There is a special command called nsenter, which allows you to enter into the namespace of any other target process, right? So you can use this to test stuff, mostly for debugging and trying out things and learning. So you can choose this -a flag is just saying what namespace system that you want to enter, right? Because I showed you there were 8 different namespace groups. So you can choose to enter all of them, in this case -a, or you can just say no, I want to only enter for as a network, from a network point of view, right? The network namespace, or I want to only enter into the mount namespace of that target process. This target, you can just target a process and enter it. And then if you run commands, so the equivalent of this is if you take the PID of that NCL in the last previous slide from outside and run this nsenter, whatever shell you will get, there again if you run psaux, the view you will get will be only within, as if it is within the container. So this command alone goes into the container, actually into the namespace, but we are, in this example, in this context, the namespace and the container are the same. Right? So I left a slide on network namespace, but it's okay if we don't do this because we're going to do this only this all day tomorrow. So we will heavily rely on the network namespace concept, right? Because that's what is, we are here in winter school on networking, right? So all this stuff we've been doing today is to build up towards what is the state of the art, what do people run. But tomorrow we'll go into exactly how the networking works internally, right? So for the kind of the rest of the workshop, for the rest of the school, you can kind of assume that a network namespace is the same as a container, right? So we are doing this because we are not interested in any of the other aspects. But at this point we don't really care about limiting the CPU or anything, right? We are only cared about the networking angle. And if we just create a network namespace on its own, is almost equivalent to a full container in our story, right? So in this example, if you just run ifconfig, it will show you the interfaces on the host. You can do the same thing inside a container, and the view you will have is completely different because it's 2 different network namespaces. And I just briefly mentioned about time. That's okay. Again, this is again another. So because we are only interested in the networking namespace, the IP command, which is our normal, go-to tool for all things networking, has an helper subcommand called netns, right? And that allows you to like run networking related stuff in different namespaces. You can create network namespaces, you can enter them, you can exec stuff in them, you can delete them, right? And we'll again rely on this heavily tomorrow to create different network namespaces, show you how the networking actually works when Docker does it, right? Or when Kubernetes does it. That's the idea. But if you're interested, you can explore this. We'll do this tomorrow. So in summary, we have kind of seen 3 main underlining technologies that make up containers. They all do different things, but they come together to build containerization. There are a lot more which we have not shown in this workshop in the school. Say about the layered file system, or say about the security aspects, right? There are a lot more things that go into making containers, but these are the kind of main ones, and these are the kind of obvious ones, right? So hopefully you got some idea of how containers work, but that's it for this session. So in the next session, post-T, we will basically kind of slightly shift gears and look into Kubernetes, right? So today you saw virtualization, you saw Docker, right? And the next step in how cloud operates, people are not directly using Docker because Docker is for one machine, right? You run containers using Docker on one machine, but the cloud is made of many machines, and you have to manage containers on many machines together, right? In a concerted fashion. You have to bring up containers, you have to be able to move data, connect between containers, you have to do a lot of things across a cluster of machines, right? That's where Kubernetes comes in, and that's kind of the next thing we'll do today. Today's session will be around just showing you hands-on view into Kubernetes, the way we saw for Docker. You'll just create some of those Kubernetes concepts at high level. Tomorrow our entire plan is kind of mirroring today's, right? So we will go into networking aspects deeper for each of these things. We'll look at containers, we'll look at how networking works with Docker just on a single machine, and then we'll also go into how networking works in Kubernetes across multiple machines, how it works, what are all the various things there. So I hope that's a summary plan. But yes, thank you for this.